Okay, students, let's begin lecture. I want to go through some. I want to go through some grade updates, specifically clicking data, and hopefully this time it's all. We got everybody in there. We're going to review some exam items that were significant items as to whether you did well or not. So that means that mathematically they're high entropy, high information. So we're going to hit those. And then we're going to finish up with some concepts about rotational kinetic energy, which is fairly simple, but I left it till after the exam. Now, the homework tonight is going to be reading, we're going to skip a few chapters and start talking about, or start studying oscillators. And then we're going to come back to the chapters that we're jumping over tonight. We'll do that in a week or so. So let's get to the updated data. Clicking data, you'll see it's muted now. Everybody's data are muted. But you'll see a bunch of data in there. The roundup figure as of 3/20, so that's before the exam. And that's a possible score of 29.29. And as always, I encode the answers in the decimal part of the roundup figure. And that's another line here. That's the cursor over here. That's this line right here. The second line on your grades page. And then we have the number that you got correct. Now remember and that's also in the whole number part of the roundup figure. So those three numbers should all be consistent numerically. Now, just to remind you, your class participation grade, 12 points out of our total of 240, 12 of those come from the answers. And we've done the calculations for that a few times. The correct is a number that at the end of the semester, I give bonus points for. So if you get 75% or more correct out of all the questions that I ask, and right now we have 29 on the books, and it should have been a little higher, but the 3 days that I was absent, you guys had to have, you weren't able to do any clicking. But anyways, if you get 75% or more correct, I traditionally give 4 bonus points for that. So that's 4 out of 240. So that's 1/60th. So that's a little bit more than 1%, which is nice. Okay, but you have to so that's like getting a B on your clicker questions. All right. Now, the other thing that I've done is tally up everybody's absences. Now, you may not have been physically absent. You may just have been late. If I ask one question and you come in late, then that's technically an absence. All right. And there's a lot of people with perfect attendance, no absences. But there's also a lot of people with a ton. All right. Now, I haven't correlated exam grades or anything like that to the absences, but I can, and I can do it easily. And I probably will by the end of the semester. Anyway, so that's on the grades page as well. And then the third thing is your actual participation pointage. Now, that's going to change by the end of the semester because we have more clicking to go between now and the final. But right now, it'll be some number out of 12, and I calculated that for everybody. Now, the difficulty that we're in right now is we have exam scores. Everybody has 3 exam scores. And now you can think about dropping your low score. So I didn't put that on the slides today, but you can make a note to yourself mentally. If you took all 3, you can now ditch the lowest one of whichever 3 grades is the lowest, and then keep the best 2. All right? Now, we have homework that I've got to get squared away, and I'm still working on that. And I know you guys are getting real antsy about the homeworks and stuff and being able to figure out your score. And believe me, I'm just as antsy as you are about that. I'll tell you what, missing a week up in New York really threw me for a loop. A solid week, not just a few days here and there tallying a full week, but a solid week straight. That was difficult. And but now on all these clicking data, they're muted right now. I want to do a few more double checks on them. I think they're all good. And the thing that, you know, the reason that, let me tell you about the clicking. We had a lot of problems with it before because the roster was not rostering up and synchronizing. So there were a lot of people that knew they were registered, could prove that they were registered, but were not on my roster on this computer. Almost everybody's on the roster now. So hopefully the data are consistent. If you feel like you have a low grade in any of the first three, then look at your absences total. Those are the days when I don't have any clicks from you. Now, as I've mentioned before, people that sit in the back, especially on that side, you sometimes will click and it won't come through. And I've warned you about that, and you're up there at your own risk. Otherwise, you know, you have to have a working clicker. So if the batteries are weak, or if it's just not clicking through, you know, that's something you've got to deal with. Right? So look at your absences. If you know that you've been here for every lecture except for, you know, February 13th or something like that, and look at your absences, and if you have more than that, then you've got a problem with your clicker. Or you're sitting too far in the back. Or you got here late and after I did one clicker question. So there's all kinds of things about that. So here's a roundup. Here's a close-up of the data. And this is the one that I was just talking about. Now, if you don't believe me that there's a lot of absences, just look here right now. Look at all the empty seats in here. Now, the official enrollment for this class is 288. All right? This room should be absolutely filled every day. Okay, that's the number of seats that we can put, you know, number of students we can put in here. All right? But that's obviously not the case. It is never the case. There's always empty seats. Now, that being the case, take a look at this. All right? There's the absence, and the way this is set up, here is the first day of clicking over here, Lecture 7, and here's last week, March 20th. Okay, I think that was last Wednesday, or maybe last Friday. What was the 20th? What's today, the 20th? Today's the 27th. So this is last Wednesday, okay? So this is last Wednesday, and there were 60-something people absent. Look at this day up here, over 100. And guess what the average is? 79 people absent on a given day. That's almost a third of the class. So if you feel like, you know, your score is low, you know, and I can't really do anything at this point. If you don't have a click on your day that you're supposed to be here, and you think you were here, and you say that you're here, and I don't have it, you know, I don't have it. You know, and it's just, you know, we got to do. I can only work with the numbers that I have. All right, so this is pretty grievous. Now I'm going to go through a few items on the exam because this curve or this chart here also explains some of the answers on the exams. Now, what we're going to do here is look at some of the exam questions, starting with this one. Alice and Bob on the merry-go-round. And what I'm doing is choosing, this is a screen grab of the instructor's statistics for exam 3. So when it closed yesterday at 3:30 p.m., for those of you that thought it was somehow due at midnight, I'm sorry, but it was 3:30 p.m. There was a handful of you. Sorry about that. Anyways, as soon as that closes, I can look at these stats. Now, the figure that we're going to look at for this one, or concentrate on, is this one at the upper right, 0.34. That's the discrimination index. Now that's a dimensionless number between 0 and actually between 1 and -1, and hopefully they're all positive. The higher the number, this is a good high one, 0.34. The more this question's answer correlates to whether you did well on the exam or you did poorly on it. So the students that did poorly overall on the exam, most of them got this one right, or wrong. The students that did well on the exam, most of them got this one right. And so anything above 0.25 is considered a good question. If you go by the discrimination index, it basically takes a ratio of the top 25%, the bottom 25%, and then the total average of everybody. All right. Now look at this carefully. Down here at the bottom, it says 76% answered correctly. All right. So this was not a hard question. But the students that didn't get it also did poorly on the exam. Now, what that tells me is that there has to be some reason for that. And this, we had two versions of this question. Basically, this one's asking, what happens when they walk toward the center. The other one was asking, what happens when they move away from the center, or can they move away from the center? Now, this question is basically asking to apply the demonstrations from last Friday. Now, we had a lot of absentee students on Friday. So if you weren't here, you don't know jack about this. If you were here, and 76%, that's pretty good. That's about our attendance rate. All right. If you were here, you know exactly what to do, because it's basically asking. The question of the test was about Alice and Bob. In class, we did the left and the right hand weights. You know what happens when you bring them in, all right? And we talked about it. But if you weren't here, God bless you. You got to come to class. It's important. That's why we have class. Now, here's another one. This one has a high discrimination index as well, 0.37. All right, now let me blow this up. Here it is, 0.37. All right, so this is even better. Now, everybody had this one. And in fact, you had two questions. I don't know if they were consecutive or not, but you had two questions about the blobs in space. And basically, this is a boxcar question. All right? So if you understand boxcars, you can understand this one. But this was a high discrimination problem. And guess what? This was not the calculation. This one was asking about the direction right here. Predicting the direction of the blob, the purple blob as it goes, after interaction. Predicting that direction. If you've been here, we've talked about that kind of thing and stuff, but if you weren't here, you're going to be flailing on that. Possible. Right, so that was a high discrimination problem as well. The calculation was okay. So when you have a calculation and then a problem, a conceptual question that is difficult enough to have a high discrimination index, what that means is you know how to manipulate the numbers and stuff, but you don't know what they mean. So that's crap. All right? So now I'm going to, at this point, I'm going to give you one more word of advice or one more bit of news. We don't have a printout to give you, like what I did for exam 1. And that's because this one's in web courses. We can't do that. But what we can do is make a list. I can download the spreadsheets of all your results. So I can look at, anybody in this classroom, and I can look up their test results and see which question they got wrong and which one they got right. Now, you can't do that because I don't release the exam. But I can do it, and what I'm going to do is produce an error list that I'll post in the grades page as a manual update to everybody's score. All right? And there's a little icon that'll appear as soon as I do that. And that'll be a list of all the, so question number 1, question number 7, question number 11 and 12. You might have gotten both of these. Now, these might have been 11 and 12, and you got them both wrong. You know that you can study for the final on this stuff. So I'll be publishing that, and then I'll publish a blurb sheet for each of the items. And actually, we're going over a couple of the items verbatim here on the YouTube. But I'll publish that for you in the next week or so. It's a big, big job because I have to do it for everybody. I have to do this big, ginormous spreadsheet, and then I have to cut and paste your set of errors, the numbers for each problem, and paste it into your gradebook page, which is tedious, and for a class this size, it's going to be a big task. But I will do that for you, and so you'll be able to have that to study for the final. Here's another one. Now look at this one. 0.30 for the discrimination index. So this is considered a good question. But look at the percent answering correctly, 43. Now this is a high entropy question. It's difficult and it is discriminating. So this is a question that if you got it right, it's highly probable that you also got a lot of other questions correct and have a high score. All right? Now the thing about this is, what's the question? Give me a...
Would you be able just to upload, like, make the answers available on the courses?
No. No.
Like off the exam?
No. We used to... Make yourself at home. It's nice. We used to be able to do that in the old Blackboard system, but you can't do it in Canvas. Maybe one day Canvas will allow us to do that. And I used to be able to publish as much of the question as I wanted, the diagrams that go with it, and so you could see your score and the little feedback, but not the verbatim question itself. But I can't do that. I have to make the blurb sheets myself. Now, let me... Shh. I hear a little bit of uneasiness. This was also an item directly from lecture. It was also in my annotations. And as I've mentioned before, if you're not studying my annotations as I annotate, and certainly if you're not studying them before an exam, God bless you. But you should be doing it. You can't get it by osmosis. Now I want to point something out here. Look at those horizontal bars to indicate 19%, 1%, that's the little one, 19%, 43%, and 36%. So there was a mixture of questions. The people that knew what they were doing, 43% answered that way with the correct answer. But there was a little bit of confusion or uncertainty, and that leads to a spread of answers into the other options. All right? So this one's not just a, this one's not just a cinchy question. It's a difficult question. All right? And there's a little bit of variation in that. Now, I want to draw your attention to option B. Here it is. Calculating the subdimensional size of a planet's atmosphere. Now, whoever, I don't want to, I'm not going to look at anybody, and I don't want to disrespect you. But if you answered this, this is about one step higher in plausibility than a Chuck Norris answer. Or, like when I'm doing clicker questions, I'll put in some, if I run out of options, I can't think of a fourth option, I'll say something about Justin Bieber or Chuck Norris or, you know, Cheetos or something like that. And you always know, okay, that's not, you know. And sometimes they'll make them obvious. But what I want, if you think about it, and, you know, and I don't put this in there to be disrespectful to students, but when you're writing a multiple choice test, if you think about it, first of all, you got to have the right answer in there. Okay, so you got to have that. And then you can't have Chuck Norris answers for the other three options. You know, or Cheetos or French, you know, all those phony ones that everybody knows automatically, okay, that's out, that's out, that's out. This has got to be the only one that's plausible. Okay? You got to have tempting answers. All right? So subdimensional size is gibberish. That's me double talking you. But planet's atmosphere, oh yeah, that's, you know, Kepler's law, planets, yeah, you know. And the other one was something about the dimension or the diameter of the sun or the circumference of the sun or something like that. All right, so that's tempting. You know, so I have to write some false answers in there, but they have to be a little bit tempting. Now, if whoever was, and this one, only 19% of the class was tempted. But in this class, that's about 52 respondents. Right? So 52 people, you know, I can identify whoever did answer this one, but I'm not going to look at the class. I'm just going to say that this one was flailing to answer this one. It's just, you know, the other ones were semi-acceptable, but that one was very rough to see. All right? And especially since we reviewed it in lecture and in the annotations, it tells me that at least 52% of the students didn't come to lecture, didn't look at the YouTube, and didn't read the book. You know, I can't help you with that. And they guessed themselves out of it. Now here's another one. This is the highest one of all. Okay? The moment of inertia brain burner. And I knew this would be a brain burner, and it turned out, you know, the discrimination index indicates that. Very high discrimination index. So the students that did really well on this test also were able to savvy this question. Now we're going to go over this when you might want to take some notes. It's basically a solid metal disc, but made of two different kinds of metal. The gray metal and the white metal. And I said that a full disc of the gray metal is half the mass of a full disc of the white metal. So basically, a half as dense, the gray material. All right, now that's down there in the list, number 1 and number 2. Now, to do this question, you had to know this, specifically the disk moment of inertia. And that was given to you in the, you know, we didn't have a cover page, but it was at the top of the, you know, the instruction set. It's at the top of every question. All right? So you have to use 1/2 mr squared on this problem. But the thing about it is we have two disks. All right? So now the gray disk, the white disk is just 1/2 mr squared. All right? And whatever the mass is. But the gray disk is 1/2 mr squared, but for a different mass. In parentheses here, right here, that's the different mass. A gray disk is half the mass of whatever the white disk is. So that's effectively 1/2 m. And therefore, the moment of inertia of this disk compared to the other disk, the white disk, the full disk, is 1/2 mr squared. A gray disk, a full gray disk, is 1/4 mr squared. All right? Now, that's for a full disk. But we don't have full disks in this problem. We have a half disk. We have a half of a gray disk cut up into quarters. And we have a half of a white disk cut up into quarters. All right? So your gray disk is a half of a full gray disk, which is 1/4 mr squared, m being the mass of the white disk. So that's a total of 1/8 mr squared. And the white half the white disk is 1/2 of 1/2 mr squared. So that's 1/4 mr squared. Now, why is this important? This again shows that the distribution of mass affects that fraction in the front. You know, how you have your mass distributed. And for instance, the Earth. The Earth is a sphere, but it's not a sphere of uniform density. So 2/5 mr squared is not, 2/5 mr squared is righteous for the Earth, but if you were calculating it pixel by pixel, you'd have to be very careful because the core of the Earth is much more dense than the mantle, and that's more dense than the crust, and then the crust is more dense than the very surface rocks and water and the oceans and stuff. So, so this is a, you know, so your total moment of inertia on this one was 3/8 mr squared. All right, and a good fraction of you got this correct, and if you did, then if you remember that you got this, well, you don't know. If you remember that you chose 3/8, you're good. Otherwise, you know, you got that one wrong. Now, is there a question? Do you want to ask a question? Anybody want? Go ahead. Do you want to ask a question? No, with the maroon shirt. No? Good? Anybody? I mean, it's okay if you want to. I mean, that's how we learn. So.
What were the percent of people
I don't know if it's on here. I thought it was. I don't show it, but.
Because they were like 15.
Yeah, there were. It was a difficult question, but not impossible. And so let's keep going through here. There's the key move there. I mean, if you know to use half of the inertia of each disk, you got to have the right mass of the gray disk. Question.
How do you get it?
What?
How do you get it?
3/8. That's on the next page here. Come on, baby. Okay, so you have 1/8 plus 1/4. That's 3/8. So the total. So the gray, half of a gray plus half of a white is 3/8 of an mr squared. Now this one, as I mentioned, some of you had this one, same basic philosophy, except I think the mass of the blue was 1/3 of the mass of the white. But, you know, on this one, you also had half a white disk and half a blue disk. They're just cut up into, you know, 1/6 segments. All right? Now, as I mentioned, I'm going to try to get error lists and blurb sheets out for you on this, but it's going to take some time. Question over here.
Hey there, I have a quick question. So,
Hey there.
This particular question, we only really went over that concept in class on Friday before the test. So my question is, when we take the final, will we have practice examples that will be more similar that we can understand?
I think I was going over the moments of inertia the Wednesday also. But I take your point, and the answer is the blurb sheets and the error lists are going to be really important. You know, for instance, this, you might not see a disk like this, but you might see a stick divided up into 2 halves of different kinds of metal. But in general, you know, we're going to have a review. We usually have, traditionally, I have a review day, the very last day of lecture, very last lecture. And it'll be using the iClicker. And it'll be in class, and you'll do it at self-paced mode, which is kind of like taking the exam with the iClicker, except it's a review set. And I'll convert, so it might be like 20 items, and I'll convert your 20-point score into like maybe 2 or 3 bonus points. Okay, and then also, and so those will be kind of a review sheet. All right, and you know I can't tell you what's on the final, of course, you know, ahead of time, but unless I accidentally do so. But I mean, there's not going to be many secrets. You know, there's going to be a lot of F equals MA. There's probably going to be some of this moment of inertia stuff. But then the other thing that I do the last week of classes is I set up a big mega review homework assignment in web courses. And that will be similar. It'll be mostly multiple choice, maybe some calculations. And that will be a review set also to help you get prepared for the final. I'll have mega office hours during exam week for this class only. Also, Santi, where's Santi? He's not here. The SI will have a review, a big mega review, an SI review, over in the student union in the ballroom. So there's stuff that we're going to have. But yeah, I mean, it's hopefully, you know, I won't be, you know, when my son was in high school, I was astounded to see his teachers give him review sheets that were basically verbatim the exam that they took the next day. And I think sometimes UCF students are used to that, but no way that I'm ever going to do that. So the review sheets, review homeworks, review clicking in class, the last day of class, it's going to help you, but it's not going to be, you know, what's on the test. But yeah, we'll have some practice to, you know. But you always got to expect the unexpected, because remember, my goal is to see if you can think. You guys, a lot of you guys are headed to med school and PT school, and I'll tell you what. If you got to look up, if you know, if you're helping a patient that's in an emergency, a cardiac emergency, I don't want you to go looking at a damn book. I want you to know it. I want you to be able to think your way through and save that life. Now, you're not going to have to know any of this crap to save a life in a cardiac emergency room, but you're going to need to think. So expect the unexpected, because that's what you're going to have to do every day if you become a doctor or a physical therapist or something like that. Question?
There was a regrade on the test. What was that about?
The regrade? Yeah, there was one of the, this afternoon, you noticed it. Did you go down or up?
Yeah. No.
Oh, sorry. Yeah, I had the wrong, it was one of the, I think it might have been the merry-go-round question, one of the merry-go-round questions with Alice and Bob. And I had the wrong option selected as correct, so I just changed it. So some people got a point up and some people got a point down. Some people didn't get anything, so that's what that was. So it's like if I bubble in the wrong dot on the answer key, I got to go back in and do it again and regrade everything. Which, by the way, I found in one of my other classes today, a student double-checked me on something from exam 1 back in February, and I said, you know what? You are right. I'm going to have to give option B correct status as well. So I have to go back in and make a new, or modify the answer key. And for them, it's a smaller class, so it's not so hard. But I got to go back in, and some people will still have no points, but a few people will have 1 point up. But I didn't have the wrong answer on that one. But, you know, so I'm sorry. I mean, it went up by 1.
That's fine. It's just, I remember the merry-go-round, and I know when the calculations, it was, one of it was.
There was no calculations in the merry-go-round.
There was the direction, and then there was the distance. That was the blocks.
Yeah, the answer was I think I think some people had, what can they do to slow down? And the answer was there was nothing that they could do. Because they were already like this. They were already the hand weights out here. And dumping in the hand weights doesn't help you at all. It speeds you up. You know, so jumping off the thing, you know, of the options that you had, there wasn't anything that they could do. Question?
Why does dropping the weights?
Because there's no, the MR squared of the weights is gone. It's detached from the system. So the overall moment of inertia goes down, omega goes up. Right? My wonderful students. Whom I enjoy every day. And you guys don't hear that enough. But I enjoy teaching you guys. So let's keep going. Let's do a little bit of rotational kinetic energy. Well, I'm not kidding you. I mean, I can look at almost everybody in here and think to myself, yeah, it's been fun having, except there's some students that have reversible names. You know, and I still don't know what it is, Austin Martin or Martin Austin? Martin Austin. Okay. We were talking about that after class the other day. Anyway, no, I enjoy, that's why I do this. I enjoy teaching you guys. Even if I have to yell at you once in a while. All right, rotational kinetic energy. Here's the scoop. What changes, you know, the work formula for rotational kinetic energy, you know, work is the change in the kinetic energy. If you apply a net force perpendicular to the radius or tangential to the circular path, then it's going to cause the disc to rotate. I mean, if you think about it, you know, to open the door, the most efficient way is press perpendicular to the door, and you know, especially perpendicular to the line from the door to the hinge. If you press perpendicular to that, you get a fast open. Right? Same thing here. So it's, or you could say it's parallel to the change in the path delta S in this diagram. All right. Now, as you know, delta S is really R delta theta. So the work, you know, F delta S is really tau delta theta, because tau is the force times the radius, if you're on a disk like this. Now, if you're doing something else at an angle and it's, you know, you got some irregular shaped object and stuff, you know, you got to do a lot of trig. But for something like this, this basically works out. So tau net times delta theta, that's your work. That's your change in kinetic energy. All right, so that's like F delta X or F delta Y or F delta S, any, you know, any direction you may care to go. All right, so that's the work formula for rotational work that changes the, and the torque changes the angular momentum state, just as a net force changes the linear momentum state or the translational momentum state. That's the way you want to think about it. You know, net force is delta P over delta T. Torque tau is delta L over delta T. Oh, that was another one. That was a rotational analog question. I don't know how people got that one wrong. I thought that one was a give me, but a lot of people got that one wrong. It was a discriminating question. Not as high as the other ones, but. Now let's talk about the actual kinetic energy. So let's take a look at a pixel. Now every pixel of this rotating cylinder has got a little bit of mass and a little bit of speed. So it's got a 1/2 mv squared. And pixel by pixel, you know, you just, but you know, the speed of this outer pixel in gray is smaller than the speed of like a pixel closer to the center. Right now, I haven't drawn in a pixel closer to the center, but I could do that. You know, I should have done that. But anyways, a pixel close to the center is going to have a smaller v. But it'll still have some, and so you'll still be able to calculate 1/2 mv squared. Now, I want you to recall the basic idea for the moment of inertia, the sum of all the mr squareds, pixel by pixel, over all the pixels. So that's what that means. The Greek letter sigma, capital sigma, means a sum. That's a mathematical code to say, okay, mathematician, take a sum. And then the subscript underneath says, take a sum pixel by pixel. And then the argument inside the parentheses says, here's what I want you to count up. Pixel by pixel, count up mr squared for each pixel and add them all together. Right, now that's the moment of inertia. We've talked about that for the last week or so. Now in the kinetic energy case, we have a little bit different philosophy. You know, we want to do pixel by pixel, and we want to say to the mathematician, okay, sum up pixel by pixel all the kinetic energy of each pixel, because they all have some. All right? And even the pixels closest to the center, you know, we're not going to, you know, the center is a point, and the center line is a line, so you're not going to say that a pixel exists at that point. A pixel has a size, a finite breadth, width, and height, so it's not going to exist at r equals 0. There's always going to be at least like a millimeter or so of r, so there's always going to be some 1/2 mv squared out there, maybe a little bit, maybe a lot. The maximum mv squared pixel by pixel is out here at the edge, all right? And lower amounts of pixel by pixel are toward the center. And the closer you get to the center, 1/2 mv, if all your pixels are the same size, the same mass, then 1/2 mv squared is going to get smaller and smaller as you get to the center. All right, now that's all interpreted here or encoded here. Now, in reality, V is equal to omega R. So this formula here, the omega R quantity squared, that's the same as V squared. Now, this second sum, the sum of all the pixels, this is still 1/2 mv squared. But now instead of the V, I put in omega R. Okay. Now this factor of 1/2 is a common factor for all your pixels. Okay? So you have to calculate mr squared or 1/2 mv squared for the first pixel, 1/2 mv squared for the second pixel, 1/2 mv squared for the third pixel, and on and on. So why not just factor it out? And that's what we do here. Right? Now the other thing that's the same is the angular velocity, omega. V is not the same for the outer pixels compared to the inner pixels, but omega is. All right? So that's a common factor, and it's inside the square, it's inside the parentheses, and it's being squared. So we can factor that bad boy out. So that's over here. Now what are we left with? I. Now look at what we got inside here. We have m. We factored out the 1/2, but inside the parentheses we still have m, and we still have r squared. And guess what that is? Dun, 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 dun. That's the moment of inertia. So this formula here, 1/2 I omega squared, encodes the distribution of mass as a moment of inertia, as we do, you know, for all rotational systems. And then the angular speed here, omega squared, that's the analog of v squared in the over in this equation. So all these little 1/2 mv squareds pixel by pixel, if you do all the summations stuff, yeah, it comes out to this simple formula. So knowing that table, you know the spheres, the disks, the hoops, the sticks, the long rods, all those, and the plates, the rectangular plate. Knowing the inertia for all those is helpful because it allows you to figure out the angular momentum, I omega. It also allows you to figure out the rotational kinetic energy, 1/2 I omega squared. All right, so all this stuff, yeah, the inertia is encoded in there, and we can kind of do a little bit of algebra. Now, if I was, if I was like that professor on the internet, where he has those big green boards and they're like 3 times bigger than this, and they're all covered with equations. If I was like that, I would do all the algebra for this. But we're just kind of, waving our hands and talking here instead of doing step by step. But you can do step by step of all the algebra here. It'd fill up a chalkboard or two. It wouldn't be too bodacious. But it boils down to this: common factor of 1/2, common factor of omega squared. Bang! The rest of it is just good old 1/2 or good old mr squared. Moment of inertia. Questions? Okay, skip ahead to chapter 16.2 and 16.3 on oscillation. I'll see you on Friday. We'll talk about that. Read as much of chapter 16 as you feel like. But these two sub-chapters especially.
I don't know if you got my message. I sent one because I wasn't able to make it to class. I think one of the days was only due Wednesday. But I emailed it to you because I didn't want to not turn it in.
That means I've got it, so it's going to be graded by me. So,
and I guess I don't know. When I guess I'm going to set a meeting with you so I can talk about the